So let us discuss about planar graphs now. Okay, so when we say a graph is a planar graph, so you take a graph. Suppose if you are able to redraw the graph in such a way that no two edges are intersecting. I mean, no two edges are crossing. So if you are able to draw the graph in a plane with this condition, we say that the graph is planar. For example, you take K4. So if you take K4, so this is K4, right? So can we redraw this graph so that this crossing is not going to occur? Remember one thing, for drawing graph, it is not needed that you need to use the straight lines only. You can use curvy paths also, no issue. The edges can be in any shape. Okay, the edge can go like a snake also. So now what you can do, yeah, we can draw, right? So what is it? So initially you can go like this. Okay, the intersection is happening here, right? Now what do you need to do is you try to take one of this outside so that it's not going to have intersection. Okay, so let me take this guy outside. So this is how I'm going to connect these two. All right, now you see no two edges are intersecting. All right, so we say that this graph is planar graph. We are able to draw this graph in a plane so that no two edges are crossing here. Okay, so that is the definition of a planar graph. If a graph G can be drawn in a plane without any edge crossing. So we can take K4 as an example. Okay, what if I take K3? There's no problem. It is already in that form only, K3. So this is a planar graph. All right, we can directly see that. Now I'll draw some graph randomly. Tell me whether it is a planar graph or not. Yeah. So how about this graph? Is it planar? Okay, let me try. So let me do one thing. Here, this vertex instead of taking here. So let me bring it on the other side. Okay, so that I can remove this intersection. So let me do that. So this vertex I'm going to take here, right? So I'll keep these two as it is. Now you establish the connection. And next you take the rest of the vertices. These two are connected and this is connected to it and this is connected to it. So how about this one? It is of degree 2. So did I leave any edge? I hope I am just one more step away. How many edges it has? So here 1. So let me do one thing. So is this edge came? Yes, it came. So how about this, which is here, and this one, it is here. And how about this one? Yes, it came. And next, this diagonal one, which came here, and the other one, which came here. I hope we have taken care of all edges. So total, its degree is 3, and its degree is 3, and its degree is 2, 2 degree, 2 degree. So the total sum is 12. So there are 6 edges. Even here also, let us list the degree sequence. So the degree is 2, degree 2, and it is degree 3, 3. This is degree 2. Yes. Now just we are one step away to show that it is planar graph. So without confusion, I would like to label this graph A, B, C, D, E. Now this is E. We kept A, B, C, D as it is. So the only thing I need to do is I need to take the C here. So let me take it. So you C, take it up, E, keep it there. Take D upside. Where is D? Yeah, D also we can take it up. That's better. Let me draw it here. So this is D, A, B, E, and C. Now let's assign the edges. So D is adjacent to A and B, right? And E is adjacent to A and C, and C is adjacent to B and E. Okay, I hope done. See, initially you thought it is not a planar graph. This is a planar graph. Okay, and this is what planar representation of the graph. Whatever we have drawn here, so that is the planar representation. Okay, and the interesting thing is, so this is a planar graph, right? Moreover, connected planar graph. So if it is a connected planar graph, then definitely it is going to divide the region into separate parts, the region of the plane. For example, you take a triangle K3. Okay, so this is a planar graph. It is dividing the entire region into two parts. So one is the inside region. I can say the region inside this triangle and the region outside. Okay, and similarly, this planar graph is dividing region into how many parts? Region inside the triangle and region inside uh, the rectangle. All right, that may not be a rectangle here. If I draw it properly, yeah, it becomes a rectangle. So let me name it as R2, and the region outside R3. So now this planar graph is dividing the entire plane into three different regions. Okay, so you take any connected planar graph, it is going to divide the region into n number of regions, the entire plane into n number of regions. And of course, we have a relation between the number of edges, number of vertices, and the number of regions divided. Euler has given a beautiful theorem to us. The relation between the number of edges, number of vertices, and the number of regions divided. Okay. First, let us do one thing. Let us think of some examples first. Yeah. So how about this example? How many regions we got here? You can say 1, 2, 3, and 4. So this planar graph is dividing the region into the entire plane into 4 different regions. You can see some of the pictures here, I mean some of the graphs. This we already worked K4, and we showed that it is a planar graph. So it is planar graph. So how about this one? Is it planar? The second picture that you're seeing here. Yeah. So what is the planar representation of this graph? So this is how we can redraw that graph, right? So now no two edges are crossing. All right, therefore it is a planar graph. So similarly, how about this picture? Is it a planar graph? The third one, there is a thumb up. Okay. Oh, there is one thumb down. Fine. So is it planar or not? The third one. Okay, let me just concentrate on the third one. And then what else I need to establish? Where is B? B somewhere I have to take. B is adjacent to A, B, and E. Okay. A is here. A, B, E. All right. Let me take this here. Is it adjacent to C? No. C is of degree 3, and this is of degree 4, and this is of degree 3, and this is 4, and it is 4th degree. A we got 4 degree, fine. How about C? C I didn't. C it is third degree, so something is missing here. What is missing? C is adjacent to A. C is adjacent to B. Oh, C is adjacent to B. All right, now why do I need a line? Fine. So let me connect it like this. C is adjacent to B. Okay, so I established connection like this. Okay. Now let me see the degrees. The degree of C is 3 now, and the degree of E, this is supposed to be 4. 1, 2, 3. So what else is missing? E is adjoined with B also. I'm having a trouble here. So this is one. Okay, there is one more picture came. There is AD also. All right, AD you can take it like this. If there is AD, there's no problem. So this is B, A, D, C, E, and A to C, and then A to E. Okay. So now you can see K33 here. So K33, is it a planar graph? So it is not. Okay. So now how do you show that it is not a planar graph? Okay. So we will take help of regions to show that this K33 graph is not a planar graph. Now what we will do is, first we will take the vertices which creates a circuit like this. Okay, V1, V5, V3, and then V4. So now this circuit divides the entire plane into two parts. One is the region inside this plane, inside this circuit, and the region outside this circuit. It's divided the region into two parts. Okay, and next you take one more vertex inside it, right? For example, what are the vertices adjacent to V1, adjacent to V1 or V4, V5, V6? Okay, or you take the vertices which are adjacent to V4, which is V1, V2, V3. All right. So now let me take one guy here inside it. Either you take one of V1, V2, V3 or V4, V5, V6, anything you take. For example, if you take V3, all right, now V3 which is connected to V4 and V5. So now what happens? Now again, if I take a vertex here and the edges incident with it, now it divides this region into two parts. Okay, like it is shown in this picture. So far we covered how many vertices? I hope we covered 5 vertices. All right. Now we are left with one more vertex. Now where do you keep that vertex? So what is that one more? V6, right? So now where to keep this V6 so that no intersection is going to occur? Suppose if I take V6 here, then V6 is connected to V3 and it is connected to V1 and it is also connected to V2. Now to connect this to V2, I need to cross this edge. Then only the connection is possible. So this is not a suitable location for V6. Now let me try it on another region, that is R22. So if I take it here, okay, you can easily establish connection to V3 and V2, no issue. But how do you establish connection to V1? Either you have to cross this edge or this edge. Okay, here also not possible. Next, let me try it on another region, that is outside. So here. Now if you keep this outside, then what happens? It is connected to V2, there is no issue. The connected to V1 also not issue. But how do you establish connection from V3 to V6? Without crossing any edge here, you can't move from inside to outside. Okay, why? Because V3 is, sorry, this is V6. This V6 is outside and V3 is inside. So you have to come out of this rectangle by crossing at least one of the edge. Okay, so this way we can show that this K3 is a non-planar graph. So this K3 is a non-planar graph. It's not planar. Okay, so we can use this region technique to show that some graph is non-planar. Not only K33, there is one more non-planar graph, that is this K5. K5 is also non-planar. Okay, so let us try to show that. So let me consider this triangle, that is D, just a minute, A, B, D. Okay, and I'm taking C inside of it. So inside of it I'm taking C. Now C is connected like this. C is connected to A, C is connected to B, and C is connected to D also. Alright, so far it is planar only with the 4 vertices. But we have one more vertex here. What is that one more vertex? E. Now where do you keep E? Total how many regions are here? 1, 2, 3 and 4. So one of these 4 regions we need to take this E. So I'm not allowed to take outside, because if I take it outside, how do you establish the connection between C and E without crossing or without going outside of this triangle? So it's not possible. So outside is not a suitable location. Okay. So E I'm not allowed to take outside. Okay. Now let me take it in the region 1. So if I take it in the region 1, okay, here, now how do you establish a connection from E to B? This is also not possible. Okay, if you take E in the second region, we get problem with A. And if you take it in third region, you get problem with D. Okay, now this says that this K5 is non-planar. Okay, so now K5 is a non-planar graph. So you write that illustration. Suppose if you take it in the region 4, right? So we can't establish connection between C and E, so that without any intersections. Similarly, you write the illustration for the region 1, 2, 3. Okay, so therefore it is very clear that this K5 is a non-planar graph. Okay, so K33, it is an example of a non-planar graph, and also K5 is a non-planar graph. Now there is some interesting fact. The fact is that suppose if you have, you take the graph, if its subgraph contains either K33 or K5, then we can say that that graph is non-planar. Okay, why? Because K33 is planar, non-planar, and K5 is also non-planar, right? Its subgraph itself cannot be drawn as a planar graph. Then how can you draw the whole graph? Okay, so let me quickly show you what is the relation between the number of regions, edges, and vertices, which is given by Euler theorem. So this is what we call Euler formula. Connected planar graph divides the region into this many number, that is 2 minus V plus E. That is number of regions divided by a planar graph equal to 2 minus number of vertices plus number of edges. Or simply you can write it like this: V plus R equal to 2 plus E. In any form you write. So this is the relation. For example, let me take K2. K2 is also connected planar graph only, no? Now, it divides the region into just one part. Okay, it's not dividing it into two parts. Okay, so we have only one region. This is all considered as one region only. Okay, so now let me verify it. So the number of vertices here are 2 and the number of edges are 1 plus r equal to 2. So r equal to what? 1. So it divides the entire plane into one region. If you have K3, you are very clear that it divides into two regions, inside and outside. Yeah. So the number of vertices are 3 minus the number of edges are 3 plus r equal to 2. Therefore, r equal to 2. When it comes to K4, how about K4? Number of vertices are 4 and the number of edges are 6. So therefore r equal to 4. So it divides the region into the entire plane into 4 regions. But when it comes to K5, it is non-planar. K5 is non-planar. Okay, how about K6? Is K6 a planar graph? Is it planar? I hope K6 has a subgraph that is K5 because by removing one vertex from K6, you will get K5. Then how can K6 be a planar graph? Because K5 can be taken as subgraph of K6. Now what is your answer now? Yeah, it is non-planar. Okay, so we don't think of K6, but you can think about some other graph with 6 vertices, which is planar. Now there is a question. I hope you can read it. If not, let me drag it down. Suppose that a connected planar graph has 20 vertices, each of degree 3. Into how many regions does a representation of this planar graph split the plane? So we know that number of vertices, so the number of vertices are 20. Okay, and each of degree 3, therefore the number of edges equal to, so 20 into 3 divided by 2, so that gives you 30. So the number of edges are 30. Therefore, what is the relation? What is the Euler formula? So Euler formula is V minus E plus R equal to 2. Alright. So now that is 20 minus 30 plus R equal to 2. Therefore, R equal to 12. So it is dividing the region into, it is dividing the plane into 12 different regions. Alright. Now let me quickly illustrate what is elementary subdivision. Okay, so don't try to read the entire thing. I'll explain you. So let's say you have two vertices and connected by an edge, U and V. Okay, now the elementary subdivision of this edge is given like this. You introduce W, one more edge, one more vertices, and then you keep it in between U and V. Now you connect U to W and W to V. Okay, so this is what we call elementary subdivision of UV. Okay, for a planar graph only we are having this elementary subdivision. I mean, we are defining this elementary subdivision. If a graph is planar, so any graph obtained by removing an edge UV and by adding a new vertex W together with an H, WU and WV. Such an operation is called elementary subdivision. See, for example, you take this graph, that is K3. Okay, and let me show you one elementary subdivision. Simple. Just keep one more vertex here. That's it. Okay, it is like on edges you are taking new vertices. That's it. This is one elementary subdivision. You can take many subdivisions. Here itself you can take one more. Here itself you can take one more. Okay. Now we are going to say that this graph is homeomorphic to K3. Why? Because this graph is obtained by taking elementary subdivisions of K3. Therefore, we say that this graph is homeomorphic to K3. Do you understand? Okay, now let us look at an important theorem to say whether a graph is non-planar or not. So now this theorem says that a graph is non-planar if and only if it contains a subgraph homeomorphic to K33 or K5. So let us look at a problem now. You see this graph. So is this non-planar or not? I'm not asking that it is planar or not. I'm asking, is it non-planar? Yeah. Okay. So why? Because you can see that it is homeomorphic to K5. So you can simply do one thing. What you can do is you can remove this K, right? You can identify an elementary subgraph here, which is homeomorphic to K5. What is that elementary subgraph? I hope you can draw the star. Yeah. Okay. So now you try to remove this K by elementary subdivision and try to remove this H by elementary subdivision. All right. And you forget about this H because you are taking subgraph. All right. That's it. Now we showed that it is homeomorphic to K5. You understand what I mean? Okay. Let me stop